Dear students, in this lecture, we are going to discuss one of the application of Schrodinger wave equation, that is particle in a potential box. What is potential box? If you take a free particle means the potential energy is zero. So it is moving freely means the potential energy is zero. In its path, there is a region exists which is having some potential energy. Particle can't move into that region. That region acts as a barrier to this particle. If that region is finite, that means that it is having finite height, then there is a chance to penetrate into that region. That is nothing but tunneling. This is also known as quantum tunneling. If the barrier height is infinite, there is no chance to penetrate into that region by the particle. Such a region exists in all the three directions, then we can say it is a three-dimensional potential box. So there is no chance come out of that box, but inside the box the particle is moving freely. In the present discussion, we are we are discussing about particle in a potential box one dimensional only. So the one-dimensional button box we have defined in what is there is a region we are taking 0 to a along the x direction is potentially 0. And before x equal to 0, including x equal to 0, the potential is infinite. And above x equal to a, again the potential is infinite. So it can be defined as a potential box of infinite height width a. So 0 to a, the potential is 0. And x less than or equal to 0, the potential is infinity. X greater than or equal to a, the potential is infinity. So we can write like this. V of x equal to 0 in between 0 to a. And V of x equal to infinity if x less than or equal to 0 as well as x greater than or equal to a. So in the region 1, that is x less than or equal to 0, the potential is infinity. So here there is no chance to get the particle. So the probability of finding the particle in this region is 0. So psi star equal to 0. Therefore psi equal to 0. The same thing happened with region 3 also. Here also the potential is infinity. There is no chance to get the particle here. So particle can exist in the region 0 to a only. That is the region 2. So we have to write the Schrodinger wave equation for the particle which is moving freely in this region x equal to 0 to x equal to a. So by writing this equation, by solving this equation, you will get the wave function. That wave function can give the information about the system. If the particle is free, what you feel, so it can occupy any position. So we have to check the particle can occupy any position in the region between 0 to a or not. And it can move with any energy. That also you have to check. It can take all the energy values are discrete. That means the energy spectrum is continuous or discrete. So for that, to explain the behavior of a particle in this potential box, you have to write a Schrodinger equation. So this is the Schrodinger equation for the particle in the region 0 to a. So in the region, the potential is 0. That's why in place of v, we are having 0 here. These are one dimensional. So we are having dou square psi by dou x square. So the Schrodinger equation one dimensional box is dou square psi by dou x square plus 8 pi square m e by square psi equal to 0. So we can replace this 8 pi square m e by h square with some alpha square for our convenience. So we can write like this, where alpha square equal to 8 pi square m e by h square. By solving this equation, we can get the solution. The solution of this equation can be written as psi equal to a sin alpha x plus b cos alpha x. Here a and b are arbitrary constants. To get these constant values, you have to apply the boundary conditions. What are the boundaries here? One boundary is at x equal to 0. At x equal to 0, the potential is infinity. So the potential is infinity means there is no chance to get the particle here. That means the probability of finding the particle here is 0. So psi star equal to 0. Therefore psi equal to 0. That means at the boundary x equal to 0, psi equal to 0. That is the one boundary condition. Same thing happened with at the boundary at x equal to a. At x equal to a also the potential is infinity. Therefore psi equal to 0. So the boundary conditions are at x equal to 0, psi equal to 0. At x equal to a, psi equal to 0. By applying this first boundary condition to the wave function, what the wave function? Psi equal to a sin alpha x plus b cos alpha x. Now we will apply the first boundary condition. That means we have to substitute x equal to 0 and psi equal to 0. So 0 equal to a sin alpha into 0 plus b cos alpha into 0. So 0 equal to a sin 0 plus b cos 0. We know sin 0 equal to 0. So this term becomes 0. Cos 0 equal to 1. So 1 into b. Therefore b equal to 0. So by applying the first boundary condition, we got b equal to 0. So by substituting this value of b here, then the wave function becomes psi equal to a sin alpha x. Now we will apply the second boundary condition to this wave function. That is at x equal to a, psi equal to 0. So put x equal to a here and psi equal to 0. Then that equation becomes 0 equal to a sin alpha a, alpha a. So this implies here a sin alpha a equal to 0 means either a equal to 0 or sin alpha a equal to 0. If a equal to 0, already b equal to 0. So if a also equal to 0, then psi becomes 0. There is no wave function exist. So system can't be explained. So you want to explain this microscope system, then you have to a should be not equal to 0. If a not equal to 0, then what will be 0? Sin alpha a equal to 0. If sin alpha equal to 0, then alpha a equal to n pi, integral of pi. Therefore, alpha equal to n pi by a. So to find the energy values, now we will square on both sides here. If you square that alpha equal to n pi by on both sides, then alpha square equal to n square pi square by a square. We know alpha square equal to 8 pi square me by a square. So substitute alpha square equal to 8 pi square me by a square equal to n square pi square by a square. Now this pi square will cancel, and from this we have to find out the energy values here. So you take h square here, so n square h square by 8m a square. So from this E equal to n square h square by 8m a square. From here n takes values, integer values, so that is 0 plus or minus 1 plus or minus 2 like this. So if you put n equal to 1, then you will get the energy value in the ground state. If you put n equal to 2, you will get the energy value in the first digest state. So here energy is not continuous. It can take some discrete energy values only. So to mention those energy values, we will put a suffix n here. So En equal to n square h square by 8m a square. So n equal to 1, the energy value is E1, that is a ground state. N equal to 2, the energy values are E2, that is the first digest state. So in this way, we can find n equal to 1, then E1 equal to this much. So n equal to 2, so E2 equal to 4 h square by 8m square. We know h square by 8m square again equal to E1. That is 4 into E1. Again, E3 equal to 9 into E1. So like this, E4 equal to 16 into E1, E5 equal to 25 into E1. That means the particle is free inside the box, but it did not take all the energy values. It can take some discrete energy values only. That means energy is quantized. The quantum value is this much, h square by 8m a square. All other energy values are integer multiple of this energy value. So now we are going to discuss how this wave function and probability distribute among the different energy levels in the potential box. So let us take the wave function here. So to find this wave function, so we already find psi equal to a sin alpha x and alpha equal to n pi by a. So now psi equal to a sin alpha replaced with n pi by a. Therefore, psi equal to a sin n pi x by a. But here we don't know the value of a. If we get the value of a, then we will get the complete wave function. Then we can discuss how this wave function distribute among the different energy levels in the potential box and how the probability distribution takes place. To find the value of a, we are applying the normalization condition. So what is the normal condition? Integral minus limit plus infinity psi star dx dy dz equal to 1. This concept we have discussed in the lecture 3. So now our potential box is one dimensional. So the region is one dimensional. So single integral is enough. And the potential box is just like this. 0 to a, the potential is 0. Below 0, the potential is infinity. So here there is no chance to get the particle. And above a, also the potential is infinity. So here also there is no chance to get the particle. So you have to search the particle in between 0 to a. That's why the limits are 0 to a and psi star, and we are having only dx because the box is one dimensional. So the normal condition becomes integral 0 to a psi star dx equal to 1. What is the psi value? A sin n pi x by a. What is the psi star? Complex conjugate of psi. But here the psi is a sin n pi x by a. It is totally real. There is no imaginary part. So the complex conjugate of real number is same number itself. So psi and psi star also same. That is a sin n pi x by a. Therefore 0 to a sin n pi x by a, and psi star also a sin n pi x by a dx equal to 1. If there is a imaginary part is there I can be replaced with the minus I. So here we don't have any imaginary part. We are having only real part. So the same number itself. Therefore, integral 0 to a sin n pi x by a sin n pi x by dx equal to 1. This becomes a square sin square n pi x by a dx equal to 1. So a square is the constant that can be taken out of the integration. But sin square n pi x by a, if you want to integrate, we are using the relation sin square theta equal to 1 minus cos 2 theta by 2. Sin square theta equal to 1 minus cos 2 theta by 2. By applying this one, sin square n pi x by equal to 1 minus cos 2 n pi x by e by 2 dx equal to 1. So here, this 2 also can be taken out from the integration. Then integral 1 dx x. Integral cos theta, the sin theta. So by integrating this one, a square by 2, integral 1 dx x, integral cos 2n by x by a, that equal to sin 2n by x by a divided by the definition of this function, that is 2n pi by a. Sorry, this x is not there. So now we are applying the limit a first here. If you put a here, so x equal to a, and here you put a here, a will cancel, then sin 2n pi equal to 0. So that it becomes x minus 0. If you apply the limit 0 here, this term becomes 0, and here at x equal to 0, sin 0, 0. So finally what we are having, this we are having only small a only by applying. So that becomes a square by 2 into a equal to 1. So this implies a equal to root 2 by a. So what is the final wave function? The final wave function is just replace this a with root 2 by a. So the wave function becomes psi equal to root 2 by a and sin n pi x by a. Psi equal to root 2 by a sin n pi x by a. Now we are going to discuss how this wave function distribute among the different energy levels and how the probability distribution takes place here. So to express that one, then we are taking a potential box here. Here n equal to 1 first energy level, and second energy level, third energy level. So in this potential box, we will discuss how the wave function distributes here. And we will show one more figure here. There we will discuss how the probability distribution will distribute here. So we will take n equal to 1. We already derived the wave function, that is psi n equal to root 2 by a sine n by x by a. Just now we derived. So first energy level means n equal to 1. So here you put n equal to 1. Then you will get wave function psi n. Psi 1 equal to root 2 by a sine pi x by a. So now how this distribution takes place in between these two. So put x equal to 0. Here you put x equal to 0. Then this becomes a sine 0. So sine 0 equal to 0. So here we will have the 1 point. And x equal to a. Put x equal to a here. A will cancel. Then sine pi. Sine pi 0. Again it is here. So if you observe this function here, if x equal to 0, this function value becomes 0 first. If x equal to a, this function value becomes pi. Okay, so if you put x equal to a will cancel, this function value becomes pi. That means the sine value varies from 0 to pi. We know the sine wave is like this. So 0 to pi means only this portion will come. So here the function varies from 0 to pi. That's why here we will get the. So what about the probability distribution? Same function. Here it is a square. So here this value is root 2 by a. So this one becomes 2 by a. But here if you observe, this is the probability density is high means this is the most probable position. What is the most probable position? This is the most probable position, A by 2. That means if energy is even, the most probable position of a particle in the potential box is center of the well. That means most probable position, that means the more chance to find the particle is at the center of the well if energy is even. That is at A by 2. And if you take n equal to 2 here, then put n equal to 2 here, then we will get psi 2. The psi 2 equal to root 2 by a sine 2 pi x by a. So you put again at x equal to 0. So at x equal to 0, this becomes 0. So sine 0, 0. So this function becomes at x equal to 0, 0. So sine 0, 0. And x equal to a, put x equal to a will cancel. This becomes 2 pi. And sine 2 pi again 0. But here this function value varies from 0 to 2 pi. So we will get a total complete wave here. So that is like this. Then what about the probability distribution? The probability distribution always positive here. That will comes like this. So if you observe the probability of finding the particle in the energy level E2, that means if the particle is moving with energy E2, the most probable points are these two here. So this one and this one. That is A by 4 and 3A by 4. Most probable points are here A by 4 and this one is 3A by 4. If you take n equal to 3, this wave function comes like this and the probability distribution comes like this. These are the most probable positions. In this way, we can locate the position of the particle. We can estimate its energy. So the Schrodinger equation can explain the behavior of the particle in this potential box by estimating its position as well as energy. If these two parameters are analyzed, we can completely analyze the system. So with this, this module 1 is completed. In the next lecture, we are going to discuss about the problems from quantum mechanics. Thank you.